Okay, so we're going to talk about 10.3, which is our geometric sequences and series, and kind of expand on what we've talked about with arithmetic. So before we've looked at arithmetic sequences where we have a common difference, so we're going up or down by a common value. Now we're going to look at a geometric sequence and a geometric series. So the critical difference between arithmetic and geometric is geometric is going to have a common ratio, so it's going to go up or down based on a multiple. So it could be multiply by 2 or multiply by a third, and that's going to be what defines the next term. So here's an example of a geometric sequence, and so we can see that we have a common ratio that we're multiplying by some value. So for this one, my common ratio is 4. If I take any two consecutive terms, so if I was to take this term and divide it by the previous term, we can see I would get 3 times 4 squared over 3 times 4, and everything cancels except for a 4. And so that becomes my common ratio. Another way to think about it is the way that I get from one term to the next is I multiply by 4. So either way that you want to think about it is going to be fine. The critical part is that we're not adding or subtracting a value. What we're doing is we're multiplying by a number, and that will get us to the next term. And so what we see here is our general formula for this is a sub n is the first term times the ratio to the n minus 1 power. And what we can see is when I have an n equals 0, when n is 1, I have a 1 minus 1, and so this term at the top here is going to become a 0, and then r to the 0 is not 0 but 1, and I'm just left with the first term, which is a to the a sub 1. So that's how that works when n equals 1. All right, so that's our setup, and we're going to go through the different kind of mechanics of how these work. But again, keeping in mind that we're multiplying by a value. All right, we're going to look at different types of summation notations. One thing to keep in mind is when we say sequence, it's just the order of the terms, and then a series, just like arithmetic, is when we're going to add up all the terms within that sequence. So again, the addition component is going to use our sigma notation and the difference between our sequence and our series. All right, so let's look at an example. All right, if I want to determine the common ratio between the next terms, what that means is I'm basically going to take any consecutive terms. I know that I'm multiplying by some r value. So if I do 9 divided by -6, I should equal my r value. I should get it back. And that's what it's going to do. So let's go through and kind of look at how these pieces work. All right, so to find the common ratio, again, I divide any consecutive terms, and I get 9 divided by -6, or -1.5. That's the ratio between them. Now, if I want to generate the next terms, what I'm going to do is take my r value. So this is times -1.5. The next one is going to be times -1.5, and I could keep multiplying by 1.5 as much as I need to generate the terms in the sequence. So again, as many as I wanted to, if I did 3 of them, I'd just multiply by 1.5 that many times, and I'd generate my sequence. All right. Let's see that I wanted to, again, I have another one where I determine the common ratio and find the next terms. This one has a variable in it. It has an n value, but it's the same process. This is a sub 1, this is a sub 2, and if I do a2 divided by a1, by definition, that's going to give me my r value. So that's all they've done over here. We have our division, we have our expressions, we have to be careful with our the way that we are factoring, right? So these are all, this is divisible by 81, this is divisible by 243, n minus 3 on the top and the bottom are going to cancel, and so what we'll be left with is just -1/3. So that becomes my r value. That's the common ratio between them as we move them forward. So we can do that to generate the next terms by just multiplying by -1/3. All right. So again, that's all it does. It takes those values, multiplies by -1/3, and gets another expression in terms of n. All right, so it's your turn to find the common ratio and then find the next three terms in the geometric sequence. Again, if you take the consecutive terms and do the division, you'll get your R value and then use that R value to generate the next terms. Okay, so now we're going to go back and use the expression, this idea of our nth term of a geometric sequence. One thing to keep in mind is that we have an n minus 1 power here, so the first term, we always start counting n equals 1, but we're going to take 1 power less than that for our ratio as we generate terms. All right, so this one is going to ask for an explicit and a recursive formula for finding the nth term of the sequence. And so if we are looking at this, we're trying to figure out what are we multiplying these by to get to our next term. So if we were to look at our terms, again, this is a sub 1 and then this is a sub 2, and I would do a2 over a1, that's going to be 2 divided by negative 1, which is negative 2. So that's my R value, and I can see if I take 2 times negative 2, if I divide by negative 2, that's going to generate the next term, which is negative 4. So I can use that and use my general expression, right? So I have my R, I know my first term, and then I have just my n minus 1, and that will generate my geometric sequence. And then the recursive piece, we basically just have to look at how do we define it in terms of the term that's previous. So that's what we're going to do here as we look at it. All right, find the common ratio. We divide, we get negative 2. And so then what we see is that we have our common ratio of negative 2. To get into formula for our value, again, this is our common ratio. This is our expression for the nth term of a geometric sequence. We've figured out A1, it was given to us. R, we just determined. A sub n, right, we just plug those values in and we get an expression. So recursive, we're going to get our first term and then indicate the next term in terms of what it is for the previous term. So for recursion, the next term is just the one that was before it times negative 2. That's all it's looking at. So it's a different way to express the same sequence, but this is the one that we're going to focus on using our geometric sequence to move forward with it. All right, so I want you to try to find an explicit formula for the geometric sequence and then try to find the recursive one, given that you have these expressions. So again, find your common ratio with division. You know your first term is 3, and then from there you can get your expression for the formula. All right, so I want to find the 11th term of a geometric sequence. There's a couple ways to do this. First is this is my first term. I can just basically multiply up, and that'd be okay unless I was trying to find like the 100th term, and then I'd have to multiply for a long time, and it would take a lot of time. So what we're going to do is a little bit better solution of using the information here, generate the expression, right, the equation for the geometric sequence, and then use that where n is 11 to figure out where our value actually is. So again, we find the common ratio. We get negative 0.95, and then from there I can generate the expression. So my expression using our formula a sub n is the first term r and I plug those values in, and what this gives me is when I put in n equals 11, I just have to plug through one thing and I get my value. So that's a lot easier than counting up from the 3 terms that I have to the 11th term. All right, so you're going to do the same thing here. Again, you heard the 25th term. Don't just multiply this out 25 times. It's going to take a long time and you'll mess something up. What you want to do is find your ratio, take your first term, get your expression, and then let n equals 25 to generate that term. All right, so what we're going to see here is that we've been given consecutive terms as we go through this, but what we can do is we can take basically if we have any 2 values of our geometric sequence, we can use that to generate the rest of the sequence. So if we have non-consecutive terms, these are going to be our geometric means, and basically what we're going to do is, as long as you know how far apart they are, that I know that this is times r, this is times r, and then I do one more times r, and I can figure out just with like 480 r to the third has to equal negative 7.5. So I can solve for r using that I know that they're going to have a common ratio. All right, that's what they're going to try to do down here. They have an expression, right, and they know r to the fourth, but we really figured out 4 minus 1 is 3, and so we get the same piece there. So that's going to allow us to solve for the R value when we don't have consecutive terms. Okay, so same idea here. What we're going to do is start off with, I know that to get to here, that's times R, and then times R again to here, and then one more times R. So I'm going to get some expression, some power of R that gets me from the starting value of 264 somehow to the ending value. And if I just look at it, I can see it's gone from 264 to 1.03125. So R is going to have to be less than 1. We're getting smaller and smaller and smaller. All right, so that's what it's going to set up. All right, I can count my n values. I know that I have 1, 2, 3, 4, and 5. That's where this n equals 5. And so we use our formula to generate what that R value has to be. Use the general expression, plug in what we know, and then from there we can figure out what our R value is. All right, so basically I figure out that it's going to be 1/4. All right, and so from there I can generate which one makes the most sense. I have two different ones because I have a square root. I have a plus or minus 1/4, and as I go through it, we have our values, and then we go from there. All right, so again, the key part is setting up the first part, determining R, and then using that value to generate your other expressions. All right, so you are going to figure out how this works, right? You set up your expression where you have a geometric sequence, and you have 20 and 8.4375, and there's 2 spaces in between there. All right. One of our last concepts here is how do we actually take this sequence, turn it into a series where we're adding values up. There are 2 expressions for a formula for a, where we have a summation. So one is if I just know R and I know my value of n, and then one is where I know the last term, so a sub n, and I know R. All right, and so we're going to use both of these depending on what the information is that we've been given. So if I want to find the sum between the first 11 terms, 11 is going to be an n value, and then I need to find my ratio between these and then plug it into the correct formula. So from here, we find the common ratio, we divide the 2 terms, negative 1.5, and then I have n, so I'm going to use my, I don't know the 11th term, right? I don't know what that value is down here, but I know that it has to be n equals 11. So I'm going to plug that into my expression, and the R value that I have, see again, I know that n is 11, and then from there I just simplify and I get 140. All right. For the next one, I know the n value, right? I know that I don't know how many it is, but I know what the last term is, and I know R. So that makes more sense to use the second formula where I have the first term, the last term, and the R value. I just plug those values in, and I get an expression of negative 131,000. All right, there's my answer. So you are going to do this one. You know n, you know 8 terms, you don't know the nth term, so you figure out which expression, which formula you're going to use where you have an n value and not a sub n. All right, last piece is using our sigma notation to determine what we have here. Again, when we're looking at our sigma notation, this is my start, that's my stop, that's my expression. So one way to think about this is we can look at it and determine what we're multiplying by every time. Well, I can see I'm multiplying by -2, right? I could figure out my first term where n is 3, and I can figure out my last term where n is 8. So you can do a little bit of work between there if you want to get your expression to look how you want. So what they're going to do is they're going to use formula 1 because we know our n value. It's not as straightforward as just using 8, okay? Because we didn't start at 1, we started at 3. So I know that 8 minus 3 plus my 1 more is going to be 6, and so that becomes my my upper bound minus my lower bound, gives me how many terms are in there. And if we were to just count them up, right, so n equals 3, 4, 5, 6, 7, 8, right? I'm getting 6 terms. Those are the things that I would get in my expression. And so when I am subtracting them, I want to make sure that I've accounted for that and I get my 6 terms there. That's where the 6 is coming from. All right, so I know r is -2 just because I'm looking at what the expression is there and it was multiplying by, and I can use my formula to determine what I have. All right, plug it in. I know n is 6, I know r is -2, and then I get 168. And there we go. All right, you need to do this one. Again, think about how many terms you have in there, looking at your lower bound of 3, your upper bound of 7, and then what your ratio is going to be given this expression. All right, last thing is when we have an infinite series. So it is possible that if we let something go to infinity, that we actually get a value. And the way that that's going to have to work is that I get an r value that's less than 1. If r is bigger than 1, I'm always going to be growing, right? So I'd have, if r is 2, I'm just going to double it, and my expression is just going to go to infinity. I'm going to get bigger and bigger and bigger. But if I multiply by r less than 1, like a half, I'm going to get smaller and smaller and smaller and smaller. And if we go to infinity, we get something called a limit where we actually get a value that comes out. And this piece simplifies to just this expression, the first term over 1 minus r. So with these, we first off need to figure out, do we have is it possible to have an expression if this just goes forever? So I need to look at my r value. So I'm going to take 18 divided by 24 to figure that out, and I get 3/4. Since that's less than 1, right, I am going to have an expression. It's going to have a sum. And so I just use the formula that we just saw to figure out what that is, right? So I do the first term over 1 minus r is 3/4, and then I just simplify, and I get 96, right? So that one does have an expression, or does have a sum that exists because the r value is less than 1. All right, let's look at the next one. Well, I can see right off the bat that this is getting bigger, right? So if I were to do my division, right, and I get 2, right, so it's doubling every time. Well, that's not going to have a finite number as it grows to infinity. It's just also going to go to infinity. So this one is not going to have a sum for an infinite geometric series. All right. So you need to look at this one. Oh, there's another one, sorry, that we're doing. I look at my value here. It's going to infinity up here. I just need to look at this value, all right, which is less than 1. So it's going to have a sum that exists. And then I need to figure out my first term. So I plug in n equals 2, and I figure out what my first term is. All right. So there's a 1. Again, plugging in n equals 2. And then I can calculate using the formula right here. So the first term over 1 minus r gives me a value from there. All right, this is the one that you have to do. So again, you know that this is going to infinity. You need to determine if the r value is less than 1. If it is, you're going to be able to find the sum. If the r value is not less than 1, then the sum is not going to exist.